I'm Tim Hanna, WB9NJS, and thank you all for joining us in this class. This has been fun preparing for this. I'm relearning a lot of materials. Um, I do want to make sure everybody's aware of who's really making this happen. Really, it's the kind of the inland amateur radio organizations, Mendocino Auxiliary Communication Service, MAX, which is associated or affiliated with OES, Mendocino County Amateur Radio Communication Service, McCarks, and the Willits Amateur Radio Society. What that really means is just hams from all around the county have come together to make this happen. Some of us are members of one or more or all of those groups. I'm in that last category. Anyhow, what are we going to be talking about? Well, let's review the topics. There's 35 questions on the test. Last week we went through 8 of those. We covered electrical principles, components, and practical circuits. A lot of material. Tonight, I'll be kicking off with radio wave propagation. There will be 3 questions on the exam from a pool of 37. And then after the break, when I wrap up and we take a break, Steve will come back and do the antennas and feed lines. Propagation doesn't mean a darn thing if you don't have an antenna to utilize. So they go together real well, I think. So what are the topics that are in the G3 element? Radio wave propagation is the general subject. There's 3 categories. One group of questions covers sunspot solar radiation, geomagnetic fields, and stability indices, maximum usable frequency, lowest usable, and short path, long path, etc. The third group is really gets into the nitty gritty, the ionosphere. We learn about the regions and some different propagation modes. There will be 1 question from each of these 3 categories on the examination. So not a whole lot. There's a lot of material that this covers, but it boils down to just 3 questions on the exam. You still need to know the right answers. So I think many of the radio wave propagation concepts that were covered in the technician class exam dealt with radio waves in the VHF UHF range, 30 to 300 megahertz, 300 megahertz and higher for UHF. It's in contrast, the general class exam focuses almost entirely on propagation in the HF range. That is 3 to 30 megahertz as a refresher for you. And this really makes sense because the general class license offers significantly more HF privileges than the technician class license, which just has tiny little slivers with lots of restrictions. And the thing that this opens up is global communications. You can literally have the world at your fingertips, talk to somebody across the world without the use of a cell phone or anything like that. Well, something similar, I guess. But a quick review in this regard too. Radio waves, they're electromagnetic energy, the same as visible light, just at a different frequency and wavelength. And electromagnetic waves typically travel in a straight line. So if that's the case, how is global propagation possible? Well, just like light, electromagnetic waves in the RF spectrum can be reflected, bent, focused, or absorbed. What does that mean? The radio wave, and what we'll be discussing tonight, is that the radio wave path is actually bent or refracted by layers in the ionosphere. We'll talk more about that in a bit, what that is. And what happens when that occurs is the signals can be returned to Earth. It goes skyward, bounces off, comes back down. That's known as skywave or skip propagation. And the distance between the stations where your signal leaves the Earth and goes up and comes back down, that's known as a hop. That's the distance traveled. And the space between stations where that hop exists, usually you can't hear the transmitting station because the energy is going overhead, and you won't hear it down at ground level. And that zone is known as the skip zone. That's where the signals actually travel right over. And here's a graphic that I hope kind of depicts that. Let's see, here is the signal source. And you'll notice that the angle that this um, signal leaves at has an impact on how far it goes. That's one of the things. Um, a higher takeoff angle is going to come back to the Earth sooner. This is that skip zone where the signals are flying right overhead, and that's the hop. That distance there would be the hop. So the ionosphere um, consists of actually several layers or regions. Um, they tend to be between 50 and 250 miles in altitude. And when you get up that high, this is above the troposphere where the weather occurs, the stratosphere above that. This is way up there. Atmosphere is very thin and it becomes ionized by solar radiation. The degree of that ionization depends on lots of things: the season of the year, the time of day, activity on the sun, in particular sunspots. We'll get into that in a little bit. So, yeah, it's the ionosphere that enables this propagation around the world. And as I mentioned, that thin atmosphere is ionized or electrically charged by solar radiation. Energy coming from the sun knocks electrons loose in those gas molecules, causing them to become ionized. The higher the ionization level is, it refracts or bends the radio waves more strongly at higher frequencies. So if you've got a lot of ionization, you can bend those higher frequency signals back to Earth. And as I mentioned, that degree of ionization, a lot of factors come into play, but it's driven by solar energy input. So here's a look at the layers. You'll notice the troposphere down here, down where's my point? Troposphere, where the weather occurs. Above that is the stratosphere. Then above that, we get into layers of ionization layers. The very first one you encounter, the one that's closest to the Earth, is the D layer. And we'll talk about its characteristics. Above that, in the E region, which is 60 to 70 miles above the Earth's surface, and even further above that, at least in the daytime, you'll find the F1 region, 100 to 140 miles, and the F2 region, which is 200 to 300 miles above the Earth's surface. So way up there. Interesting thing happens at night. A couple of things. The F1 and F2 combine into a single layer, which is shown. Here's one, here's two. At night, they become one. So let's get into the details about these regions that you'll need to know. The D region, as I mentioned, it's the closest to the Earth. It forms in the daytime and it dissipates at night. So it's driven by solar energy. When the solar energy goes away, so does it. This is a very important characteristic of the D region. This comes right from one of the test questions. The D region absorbs signals below 10 megahertz during the daylight hours. So rather than bending them back to Earth, it just absorbs them and just eats them up. They go away. As a result, and this is from a question as well, long distance communications on the 10, 60, 80, and 160 meter bands, which covers 7 to 1.8 megahertz, definitely below 10 megahertz. Long distance communications on those bands are difficult during the day. That's because the D layer is absorbing that energy. Further frustrating on these lower HF frequencies, the 1.8 to 7 megahertz, often impacted in summer by high atmospheric noise or static right out of the question pool. Lightning crashes, other things, just atmospheric noise in general. It's higher in the summer on these lower HF frequencies. All right, let's move up. Let's go up to the E region, 60 to 70 miles above the Earth's surface. It also dissipates at night. If you actually can bounce a signal off the E region, and there's conditions where that can happen, that single hop, the from the transmitting station to the receiving station, will cover approximately 1,200 miles. That's a question pool question, single EHOP, 1,200 miles. Um, what's interesting in the E layer, and this isn't part of the test, but um, there are times, particularly in the summer, where highly ionized clouds form. They're not visible clouds, they're not water moisture, but they're ionized regions. And that can yield VHF, what they call sporadic E-skip, signals that would normally not get returned to Earth, get bounced off in the E layer with sporadic E. Okay, up to the top we go. The F region. That is the workhorse of the ionosphere, in my opinion. Um, and it's also the furthest from the Earth's surface. As I mentioned, the F1 is 100 to 140, F2, 200 to 300 miles above the Earth's surface. And at night, they combine into a single layer. Doesn't go away, it's still there. Now, the higher altitude associated with that F2 layer, what does that do? That can produce longer skip propagation than any other ionospheric region. That's the answer to a question. Higher, longer skip propagation is due to the higher F2 altitude, versus other regions. Now, and here's the numbers to prove it. A single F2 region hop is approximately 2,500 miles. Two questions in the pool regarding hop. One is an E layer, and that's 1,200 miles. The F2 is 2,500 miles, and that's because that layer is in higher altitude, further above the Earth's surface. So, a quick stat: our global circumference is right around 250. I'm sorry, 25,000 miles. Um, how do you get around the Earth if your hop only goes 2,500 miles? Aha. The signal may actually make multiple hops, and in that way can circle the Earth. Signal coming down can bounce back off and head back up to the ionosphere for another trip on that roller coaster up and back down and make multiple hops. Okay, let's do some quick questions here on the material we just covered. Which ionospheric region is the most absorbent of signals below 10 megahertz during the daylight hours? Well, our friend is not the D layer. It's that D region that's most absorbent, and it'll just suck those signals up and they disappear. Okay, I think we just talked about this. Why is the skip propagation via the F2 region longer than via other ionospheric regions, such as the E? Well, it has nothing to do with density or Doppler effect, and temperature inversions occur way below that. It's because it's the highest. The mirror that you're bouncing off is further away. You can bounce your signal further. What's the approximate maximum distance along the Earth's surface normally covered by one hop using the E region? E region is lower, so it's not going to be 2,500 miles. It's not going to be 1,200 miles. 180 is awfully short. The answer is 1,200 miles, 1,200 miles for a single hop in the E region. Okay, why is long distance communication on the 80, 40, 10, and 160-meter bands more difficult during the day? Well, it's our unfriendly friend, the D layer, and it absorbs signals at these frequencies during the daylight hours. Um, that's that below 10 megahertz where the D layer absorbs that energy. Okay, so one of the ability of signals to travel around the globe, it really presents an interesting phenomenon. Um, while signals, because there's more than one way for a signal to reach a receiving station. We're not on a flat surface. We're on a globe. We're on a sphere, and signals can bounce around in more than one direction. So there's more than one way for a signal to reach the receiving station. If it happens to take the most direct path, which is known as short path, it goes right, makes one, maybe two hops, whatever, and your signal winds up there on the direct path, the short path. But because we're on a sphere, The signals can travel 180 degrees in the opposite direction and still reach the same destination. Longer go, but that's why we call it the long path. So, some of the questions in the question pool about long path contacts include this idea that if you're using a directional antenna and you're trying to use a long path to make the connection, you would point that directional antenna 180 degrees from the short path heading. Because if you've got a beam or some antenna where you're focusing the energy and you're trying to use a long path, you want to point 180 degrees away from the short path heading. Interesting thing. Now, I've never heard this, but because the signals are taking different paths to get to the same location, one being much longer, you may actually hear a slightly delayed echo when you're receiving a skywave signal via short path and simultaneously long path. They're both there, and the signals are traveling both ways. That longer path, the multiple hops that it takes for the long path propagation, will impart a delay, and you'll hear a delayed echo. Okay, there's a whole bunch of questions in this next group, and I label it frequency-dependent responses. A bunch of terms that you'll need to know. They're not too complicated, so let's dive into them. The first one is the maximum usable frequency, MUF. What is the MUF? It's defined as the highest frequency that may be used for communications between 2 points. And I'll add to that at any given time. This is a dynamic thing. So right now, the maximum usable frequency between Willits and some location is what it is. It may change as conditions change. What affects the MUF? It's affected by the path distance. This is right out of the questions. Path distance, location, time of day, season, solar radiation, and ionic disturbances. So a lot of things can mess with the maximum usable frequency. Interesting thing to know, and this could come to be, you could use this to your advantage. The least attenuation of a long distance skip signal occurs at frequencies that are just below the MUF. So if you want to get your biggest bang for the buck, get the most signal through on that hop, try operating at a frequency that's just below the MUF. Okay, other side of the coin, LUF. Lowest usable frequency? You betcha. That's what it is. What's it defined as? It's again from the question pool. The lowest frequency that may be used for communications between 2 points, and again, at any specific instance in time. The the answers that are wrong, it put different time frames on it, hours, 4 hours, 24 hours. Nope, it's just the lowest frequency that may be used between 2 points at any given time. What happens to the frequencies that are actually below the LUF? Well, they get attenuated or they lose their power before reaching their destination. Again, answer to one of the LUF questions on the test. Frequencies below the LUF are attenuated. They don't make the trip. Okay, so what does this mean? How do you put MUF, LUF together? This is a thing to remember. When the frequencies are between the MUF and LUF, if you're above the lowest frequency and below the maximum, those are the signals that are refracted back to Earth by the ionosphere. That's the range of frequencies where you can get this skywave or skip to work. However, when the lowest usable frequency is greater than the maximum usable frequency, that's not a good condition because that means HF skywave propagation is not possible over that path. That is an answer to one of the questions. If the LUF is greater than the MUF, don't count on skywave propagation on that path. Okay, a couple other terms that come in this section. One is the critical angle, or I'm sorry, critical frequency. And what's the critical frequency? Well, the answer in the question pool says it's the highest frequency signal refracted back to Earth at a given incident angle. We'll see this here in a little bit. Um, so critical frequency depends on the incident angle, how much you're pointed up above the horizon. But critical frequency, highest frequency signal refracted back to Earth. The other one concept is the critical angle. What's the critical angle? It's the highest takeoff angle that returns radio waves under specific ionospheric conditions. So the critical angle is going to change as ionospheric conditions change. It'll change with frequency. And that's the angle that you need to um, be below if you want to bounce your signal back off the ionosphere and back down to Earth. Okay, so hopefully this picture kind of depicts it. If the frequency is too low, if you're below the LUF, that frequency is absorbed. It just doesn't go anywhere. It peters out. If the if the angle isn't right, you can actually go not be bent sufficiently and go back out into space. But if the frequency and angle are correct, right in between, your signal will come up into the ionosphere, be bent down, and come back to Earth. So all of this theoretical stuff is great, but at some point you may want to know if the band that you want to use is actually open to the regions that you want to contact. So how do you determine actual propagation conditions, not just looking at all the theoretical stuff? Well, this isn't one of the questions, but it was in the um, the concept was in the technician exam, and it's something that I do. Listen for a propagation beacon station or stations on the desired band. Propagation propagation beacon stations uh, transmit nearly continuously, typically a low power signal. I usually listen for 10-meter beacons, but there's propagation beacons on either band. So you can listen. And generally, if you can, and one caveat, those stations identify themselves with their call sign and typically their location, their grid square location, maybe other information with CW. Yep, you need to know code or have something on your phone that will decode it for you in order to determine the call sign and the location of those beacon stations. Anyhow, let's get on with the answer that's actually on this test. And you may use a network of automated receiving stations to see where transmissions are being received. There's via the internet, there's sites you can go to and look at automatic monitoring stations, and it'll tell you if a signal's heard. Quite often, this is done with digital modes like FT8. You can check and see who's seeing your FT8 signal where in the world. But the actual question that's on the exam will refer to the use of automated receiving stations. Okay, so I mentioned earlier that the skip zone is kind of a dead zone. Most of the signal is actually going up overhead, and you're not going to hear it. But there are some modes where propagation within the skip zone can occur. And there's quite a few questions in the pool about this next mode, so I suggest you get familiar with it. And that's scatter propagation. Scatter propagation, it's in the answer is a type of propagation that allows signals to be heard in the transmitting station's skip zone. Okay. And things that can influence it are reflections from the Earth's surface, the ocean or mountain ranges. They may give a little different angle um, to the signal and may return the wave back to Earth, where normally it would go all the way up to the ionosphere. It may get kind of jumbled up. The ionospheric regions are not perfect reflectors, so there can be erratic reflections from within the ionosphere that produce scatter propagation. Here come the answers. Um, the one question asked about HF scatter signals, why are they usually weak? Because only part of the signal energy is getting scattered. A lot of it is going off elsewhere. So they would tend to be weak. And because that there's some less than perfect reflection. Things might get bounced around in the ionosphere. It's not unusual for them to have an unusual sound. They might sound fluttering, or they might be sound distorted. And the distortion is because the energy is scattered into the skip zone via different paths. That's answer to one of the questions. Okay, another topic that they briefly touch on, and there's only one question in the pool. That's near vertical incident skywave propagation. What the heck is NVIS? Well, it's defined in the question pool as the short distance, medium frequency, or high frequency propagation at high elevation angles. What the heck does that mean? That means that you use an antenna where the signal is sent up nearly straight up. Not quite, but it's near vertical. And it hits the ionosphere and it gets bounced back down. So it's like bouncing a ball off the ceiling. And if you put enough angle at it, you can get it to come down, if you put the right angle, close to your feet. Okay, question time. What factors affect the MUF? Well, you better know what the MUF is. That's a maximum usable frequency. Could it be the path, distance, and location? What about the time of day and season, solar radiation, ionospheric disturbances? Man, all of those sounded good to me. All of those choices are correct. What is a characteristic of skywave signals arriving at your location by both short path and long path propagation? Well, you might hear something unique. It has nothing to do with fading at a regular 10-second interval or an increase by 3 dB. Signals might be canceled. Nah, the actual phenomenon you might hear is a slightly delayed echo because the signal that's coming via the long path arrives just a little bit later. Ooh, what's the LUF? Well, a lowest usable frequency for communications at any point outside 100 miles. Lowest one during the last 24-hour period, last 60 minutes. Nope, none of those. It is just the lowest usable frequency for communications between two specific points. No radius, no time factors imposed. That's how you find the right answer for that one. Okay, which is the following way to determine current propagation on a desired band from your station? Well, the only correct answer here, and it's the only one of this topic here, is the use of a network of automated receiving station. Go on the internet and see if your signal's being heard. What makes HF scatter signals sound distorted? Well, um, the ionospheric region is unstable. Maybe ground waves. Nah, ground waves. We haven't even talked about those. They don't have anything to do with it. E region's not present. No, that doesn't mean it's the fact that the energy is scattered into the skip zone through several different paths. There's different ways that the energy is getting up in there and it gets jumbled around. So why do they sound distorted? Because the energy is scattered into the skip zone through several different paths. Okay, coming into the home stretch here, and I like this part. Um, it's time now to discuss the engine that drives all of these conditions in the ionosphere and the Earth's magnetic field. And that is courtesy of our neighborhood fusion reactor, the sun. It takes hydrogen, fuses it into helium, and releases enormous amounts of energy. So the sun, um, it's more than just the visible light that us humans see. A lot more energy is radiated from the sun than just that. Um, There are ultraviolet and X-ray radiation that comes from solar flares. We're not going to dig too deep into solar flares, but remember that because that's part of the question. Ultraviolet and X-ray radiation that are come from the sun from solar flares. Okay, ultraviolet light and X radiation are the same thing as visible light and radio waves. They are a form of electromagnetic radiation.
So guess what? That means they travel at the speed of light, 300 million meters per second, same rate that radio waves fly through the ether at. So because it travels at the speed of light, ultraviolet or X-ray radiation from the sun can affect HF propagation on Earth in about 8 minutes. That's the shortest time period that's on the in the questions for this question. But they're booking, man. Within 8 minutes, they can affect HF propagation. That's ultraviolet and X-ray radiation because they are electromagnetic radiation. Okay, what happens when one of those bursts come along? It can produce a sudden ionospheric disturbance, and those disturbances impact daytime ionospheric propagation. And it disrupts the signals on the lower frequencies more so than the higher frequencies. So again, you get on that 160 to 40 meter range under 10 megahertz, you're going to see more impact from sudden ionospheric disturbances, more so on the lower frequency than the higher frequency, right out of the question pool. Okay, let's talk about another form of energy that's quite different. And it's fun, and I'll get into this in just a little bit, but coronal mass ejections. The sun has a very violent surface at times, and there are coronal mass ejections, or CMEs. And what do? Well, they are actually the source of what's known as the solar wind, which is a stream of charged particles coming from the sun. It's plasma. And a CME can generate a huge plume of plasma. And if it happens to be pointed at Earth, it will get here and can have impacts. But it's not electromagnetic radiation. It's charged particles. It's plasma, and it does not travel nearly as fast as ultraviolet or X-ray. Um, and as a result, it takes from 15 hours to several days before the energy from a CME affects radio propagation on Earth. Okay, let's look at how these sources of energy impact the ionosphere and other regions. The ultraviolet and X radiation, what we've been talking about all along, they interact with and energize the ionosphere. It's the energy from this radiation that's knocking those electrons off those gas molecules up in the thin atmosphere, and causes them to become the ionosphere, become ionized. Coronal mass ejection, CMEs, totally different story. That plasma stream interacts with the Earth's magnetic field, not the ionosphere. That plasma stream impacts the Earth's magnetic field, and it can trigger what's known as a geomagnetic storm, defined in the question answer as a temporary disturbance in the Earth's geomagnetic field. So that plasma stream from the CME could trigger a geomagnetic storm and temporary disturbance. Geomagnetic storms affect HF propagation, not in a good way. Depending on the intensity of the geomagnetic storms, and there's scales for that. It can cause a degrading of high latitude HF propagation. So you get up north, maybe above the 45th parallel, or even higher, and you'll start to see some degrading of the HF propagation due to those geomagnetic storms. Long distance communications, again, this is from the question, long distance communications affected by charged particles reaching the Earth's surface from coronal, what they call solar coronal holes, same thing as a CMA. HF communications may be disturbed. So again, not our friend, at least not on HF. Geomagnetic storms can mess things up. But one of the neat things is high geomagnetic activity, these geomagnetic storms can trigger aurora, visible aurora. And if you haven't seen them, they're a sight to be seen. But the neat thing is you can actually reflect VHF signals off of the aurora. So this is the only instance in all the questions where high geomagnetic activity can have a beneficial impact on propagation, but not HF propagation, it's VHF. Okay, our buddy the sun. Am I missing my questions here? Maybe I'm not. Anyhow, the sun is very, very dynamic, and is closely monitored from observatories on Earth and numerous satellites. Um, the sun goes through a long-term cycle, a sunspot cycle, that repeats approximately every 11 years. We are right now approaching the maximum, maybe in a year or so, of cycle 25. So right now, the sunspot cycles in general are increasing as time, or sunspot number of sunspots are increasing. And from the questions, the very first question in this category, the number of sunspot. Oh no, it doesn't. I'm sorry. Wrong page. Number of sunspot goes from a minimum to a maximum in about 5.5 years, and then it drops back from that maximum to the next minimum in the next 5.5 years. So this is the one I was talking about. The sunspot numbers, higher sunspot numbers, generally have a represent a greater probability of good HF propagation. There's no guarantee, but higher sunspot numbers, greater probability of good HF propagation. On the other hand, if you find yourself in the solar minimum, the least reliable bands during periods of low solar activity are those higher frequency bands, 15, 12, 10-meter bands. Get up in the higher part of the HF range, um, those bands don't produce well during low solar activity. We're on the upswing. Propagation on those bands is picking up. Fortunately, the 20-meter band supports worldwide propagation during daylight hours at almost any point in the 11-year cycle. Um, unlike the higher or lower frequencies, you can just about count on 20 meters during daylight hours anytime during the 11-year cycle. Okay, solar parameters. They are measured and they are reported daily. There's numerous websites where you can go and look up the latest solar data. I do that weekly. One of the things you'll see reported is the K index. And in the question pool, you'll be asked, what does that represent? The K index is a measure of the short-term stability of the Earth's geomagnetic field. Excuse me. Now, when the K index is 3, there might be a mild geomagnetic storm. If it gets up to 5, yeah, it could be some visible aurora. If the K index gets up around 7 or 8, you're looking at a pretty whopping geomagnetic storm with the possibility of visible aurora as far south as California. Okay, K index short term. The other index that might be reported would be the alpha index. That's the long-term stability of the Earth's geomagnetic field. In the questions, in the answers, you can eliminate most of them because they don't refer to the geomagnetic field. Look for geomagnetic field with K index, A index. The other item that's reported regularly is the solar flux index, and that is a measure of solar radiation with a wavelength of 10.7 centimeters. That's the solar flux. Look for the 10.7 centimeters. Um, in addition to the 11-year cycle, like I said, the sun's very, very dynamic. Conditions change on a much shorter time frame. Believe it or not, the sun's surface layers actually rotate around its axis. And this occurs in a 26 to 28 day cycle for the sun's outer layers to rotate all the way around. This can cause HF propagation conditions to vary periodically on that same cycle. That comes from one of the questions in the question pool. That 26 to 28 day cycle can cause HF propagation to vary. The neat thing about it, and this isn't on the test, but that rotation causes sunspot regions to appear, if you're looking observing the sun, and then move across that visible solar disk. They'll get to the other side and disappear. And then a few weeks later, those regions come back into view. And it's only when when those active regions are pointed at the Earth that we really get the impact of the solar energy that's coming from them. Okay, 40 minutes here. We're doing all right. Down in the last group of questions. What is a solar flux index? Well, I told you, look for the 10.7 centimeters, and that's your answer. Solar radiation with a wavelength, 10.7 centimeters. So approximately how long does it take for the increased ultraviolet and X radiation from a solar flare to affect propagation? Well, ultraviolet and X radiation are electromagnetic energy, so they travel at the speed of light. Look for the shortest time period in the answer, and that's 8 minutes. So UV and X radiation, they get here quick and can impact the propagation in short order. What is a geomagnetic storm? Sounds kind of scary. Has nothing to do with the solar flux. It's not a thunderstorm. Ripples in geomagnetic force, yeah, maybe, but it isn't. It's D, temporary disturbance in the Earth's geomagnetic field. That's a geomagnetic storm. They come in different sizes and intensities, and if the K index is high, you might have a pretty significant geomagnetic storm. So, how is long distance radio communication usually affected by the charged particles that reach the Earth from solar coronal poles? Charged particles. We're not talking X rays or UV. Well, they're not our friends. It has nothing to do. You can eliminate the last two answers. UHF ducting has nothing to do with that. That occurs in the troposphere. X those right out. So it's either going to make it better or it's going to make it worse. And in this case, those charged particles are not our friends. They will make HF communication can be disturbed by those charged particles. What causes propagation conditions to vary periodically in a 26 to 28 day cycle? Long-term oscillations, nope. Cyclic variation, the Earth's radiation belts, no. Rotation of the sun's surface layers around its axis that goes around, comes back again in 26 to 28 days. And again, this I think is an optimistic answer for this one, but how does higher sunspot number affect HF propagation? Well, there's no guarantee, but higher sunspot numbers generally indicate a greater probability of good propagation. There's no guarantee, but when you're in an active period, as we are now, with higher sunspot numbers, a better chance of good propagation at higher frequencies, at 15, 12, and 10 meter bands. Okay. Sorry for all the ads flying across there, but this is spaceweatherlive.com. That is the latest daily image of the solar disk that you see right there. And you'll see regions that are numbered. There's some dark spots, some not so dark, but each one of those is a sunspot region, an active one. And that one in the middle of 3460 is pretty well pointed to Earth. So if there were some activity there, we might get some impact from it. So yeah, again, we'll scroll up here. There's the image of the solar disk. You can see all the numbered regions. If we come down here, we've got a summary. The latest sunspot number was 129. That's down 20 from the previous day. So it was 149 yesterday. The solar flux, 10.7 centimeters, 164. That's down a bit from yesterday. So right now a little downward trend. And if you do come down here, you can see they're showing the regions and whether there's a probability of flares, and kind of a close-up of the regions. Now here's one you can see. Um, that is that 3460, the one I said was kind of looking at Earth, and you can see the regions of activity in there. So anyhow, um, it's kind of neat. I've been tracking this for a little over a year now because I was interested in the peak of the solar cycle and wanted to learn some more about it.
Tim mentioned the three inland clubs. I'd like to mention the Anchor Bay Radio Club down on the South Coast because I have a pretty good feeling that Peter is a member of that club. And Peter is going to be one of your presenters here for a couple of units coming right up. So I'd like to mention that too. This is a county-wide effort, and I think we're all doing it because we enjoy doing it and because we really love the subject. And here we are in second session with G9, and we're going to talk about antennas and feed lines. I would like to say that my particular personal opinion is that antennas and feed lines are the most important component in your station. They affect the signals you can receive, the signal strength of the signal that you send out. They can add noise, they can reduce noise. They can also pick up interference from other stations or reject that interference. So you can get a lot of benefits. And if you remember your decibels, and I hope you do because we're going to cover them again anyway, a 10 dB improvement in signal is like adding a zero behind the output power of your transmitter. Now that's a pretty big deal. If you go from 100 to 1000 watts, that's 10 dB. But you can definitely get 10 dB out of an antenna system. And sometimes you can do better than that. So without spending $3,000 on an amplifier, you can put up a few $100s worth of an antenna and do just as well. And then if you do get that amplifier, then you got gangbusters going on. So I want to point out that I'm going to cover all the questions in this session tonight. And I've put the question number in the box whenever this what we're talking about relates to a question. It may be the exact question with its exact correct answer. I'm not going to show you any of the wrong answers because I want you to memorize the correct ones. Or it could be a statement that's made out of that question and answer, or it could just be the subject matter. And at the end of the presentation, after I show the last slide, there are about 6 more slides that are the actual questions with the answers with the same numbers so you can match them up if you choose. So let's do a quick review. The antenna transforms the current into radio waves. A lot of things could be an antenna. You can have any kind of metallic object that will conduct electricity as an antenna, but we're going to talk about optimum antennas tonight. The component parts of that antenna, the radiating parts, are the elements. And the polarization is determined by the orientation of the electrical field, which generally follows the shape of that element. So if the element is horizontal, the electrical field is horizontal, and so is the term polarization for that antenna. The feed point is where your feed line connects with the antenna, and it finds the impedance there. The feed line has its own impedance. The antenna will have its own impedance, and your job is to make sure that they are as closely matched as possible. And when you have an antenna in resonance, that means it is a purely resistive load. It does not have a capacitive or inductive reactance component to it. So first we're going to start, let's look at the radiation patterns. I hope you're familiar with these diagrams. If you're not, this is the azimuth. This is your compass, basically, with 0 being north. What you can see here is that you have a major lobe over here, and you have a null back here. The difference in these circles indicates the number of decibels difference between the lobe, the peak lobe, and the null. And that's how much forward gain you have. It's also, well, from the 0 point to the extreme is then how much forward gain you have, and the difference between these two is how much front to back ratio you have. Because this, if you have a directional antenna, it allows you to point the back at the signal that you don't want to hear, and probably reduce that interference considerably. So you can gain from reducing your interference, and you can gain from maximizing your forward power. This other diagram is the elevation. Tim mentioned the critical angle and the critical frequency. The critical angle for that critical frequency is what you want your lobe to be pointed at in your antenna, whichever lobe it is. This is your horizontal direction. This is your vertical direction. This could be the critical lobe right here, the critical angle. And that is really important if you want to work that longest skip. This particular antenna also has a lobe going vertical. This is the lobe that would give you that NVIS signal that Tim mentioned, that near vertical incident skywave. It's going to go up and bounce back. Let's move on here. Okay, we're going to start with the simple dipole. You've all seen this. It is the most basic antenna. It's a half wavelength, a quarter wavelength on each side of this particular antenna configuration, which has a center feed. And that's the usual construction. 2 halves, either wire or tubing, and the feed line connected in the middle. That gives you the approximately 50 to 75 ohm impedance. Now, if you notice here, one of the questions is the feed point impedance in a half-wave dipole increases steadily as the feed point is moved from the center toward the ends. There's the question number. This diagram shows you that in the center of this dipole, you have 0 voltage, and you have maximum current. Come on back, there's your current curve. And this is the impedance. In the center, 73 ohms, 50 to 75 ohms. At the extreme, in this diagram, 2,500 ohms at the extreme. It could be higher. So the center, it increases steadily as you go out from the center. That is a sentence expressing it as the question in a positive way. And here you can see that the feed point at the end is very high impedance. Okay, back to our diagram. The antenna radiates broadside from the elements. So if the element is pointed north and south, it's radiating east and west. You will see that in the 3-dimensional version here, this is outer space, looking at that antenna element. That antenna element is radiating as a donut, which the answer in the question is a figure 8 pattern in free space. So another thing that we have to really be concerned about with our antennas is the proximity to the ground, and it's measured in wavelengths. That's where we get our interaction with the Earth. It can affect the resonant frequency of the antenna, the impedance of the antenna, both the azimuth and elevation angles of the antenna. So one of the questions, so you see here that here's a question. Impedance will decrease by reducing the height above ground. That means as you lower that antenna, the impedance that the feed line sees at the antenna junction will decrease. Conversely, if you raise that antenna, it will increase. So it's really important for you when you're tuning your antenna to try and get your antenna analyzer as close to the antenna and get the antenna as near that the operating elevation will be as possible so that you can measure the impedance at the exact location that it will actually exist at. Now, this bottom question here, the azimuth and elevation will change as the height. Somebody from the DMV wrote a question. I'm going to read it to you. This is the question number B05. How does the antenna height affect the azimuth radiation pattern? So the azimuth radiation pattern, remember, is on the compass of a horizontal dipole HF antenna at elevation angles, this yellow elevation graph, higher than 45 degrees. And the right choice is C. If the antenna is less than half a wavelength high, the azimuth pattern is almost omnidirectional. Took me a long time just to decipher that question. What they're telling you is that near vertical incident sky wave is an antenna that's at a low elevation. In this example, the purple line is a dipole that's a quarter of a wavelength from the ground. The blue line is a tenth of a wavelength from the ground. And the green line, which is way down here, is 0.03 wavelengths from the ground, which is probably just a few feet. But you can see that with the 45-degree angle, most of the energy is going vertical. This is a near vertical incident antenna. They didn't put the frequency in this question, so you had to make sure, you had to kind of figure that out. One thing I want to point out, the reason that this green elevation angle is so much less intense, see, it's 10 decibels down from the outside of the circle. That's because of its proximity to the ground. Remember, I told you, the ground would just suck up the energy. So moving on. So lower ground losses are an advantage to a horizontal antenna if you can get it up in the air as compared to a vertically polarized antenna. This is a positive answer here. This is a reconstructed question in a positive way, and you can reference the actual question if you like at the end of this. The inverted V is a very common form of the dipole, and one of the things that I'll share with you about that is it will usually have a lower impedance than the dipole that has the horizontal legs and horizontal elements because of its proximity to the ground. Okay, we have a couple of formulas here. You have to memorize one formula. My favorite is 468, but I read in this handbook that we recommended that you buy, 492 is the number to divide into the frequency to get the estimated length of the antenna. Either way, either with 468, which has always been the traditional number, or 492, you're going to get an answer that's very near 33, and that is the official answer for this 20-meter antenna. For the 80-meter antenna, you'll get an answer very similar to 132, which is the actual answer. One of the things to recommend, and the reason they're using 492 is that will make the antenna longer than you need so you can trim it and make it tune properly. And like I say, You want it to be a little bit longer than you need if the antenna starts out low, because as you raise it, the antenna will need to get longer to stay resonant at the same frequency. So let's look at the quarter wave vertical. They use a lot of different terminology in this book. They refer to it as the ground plane a lot, but a quarter wave vertical is actually just half of a dipole. And you can't exist with just half of a dipole. You have to have something else for the other half of the dipole. So in this case, the Earth or some other form of ground plane takes the place of that other half of the dipole. In this illustration here, which mirrors one of the answers to one of the questions, a ground plane can be wired on the ground or buried a few inches below. And this is a picture of a 40-meter radial field here that's being buried in the ground. The antenna is not there yet. It would be about that tall. Excuse me. You can also elevate the radials. In other words, put the entire antenna up in the air and put those quarter wavelength radials under it. If you have them in a horizontal fashion, you'll get an impedance that's a little bit lower than if you have them sloped. And here is an answer to another question. 45-degree angle gets you a 50 ohm impedance, which coincidentally matches your coax. And if you go to a full droop, like this example, you end up with a vertical dipole and a 75 ohm impedance, just like if it was a horizontal dipole. Now, in this case, because it's vertically oriented, you have an omnidirectional radiation pattern. And you also have another formula. 234 is half of 468 if you're using that formula. 234 is pretty easy to remember. Divided by the frequency, and you get an answer of B. Okay, now let's talk about directional antennas. That's where you get the bang for your buck. The elements in an array may be wire or metal rods or tubes, or a combination of that. You can see here that this is one of the questions that you'll see on the test, that this array of two or more elements is designed to focus energy in a specific direction called the main lobe. And you've got two types of elements in an array antenna. You've got driven elements and you've got parasitic elements. You can have multiple driven elements or multiple parasitics. These elements influence the radiation pattern. And I hadn't run across these terms before in constructive and destructive interference. But I found this really cool graphic that I hope you enjoy, that will visually demonstrate how, because these you've got your driven element here creating this signal. And as it moves in this direction, the directing element here, which is a little bit shorter, that's an answer to a question. The director is a little bit shorter than the half wavelength driven element. This is basically a dipole. As this energy goes off in both directions, as it passes the director is shorter and it tends to match the phase. It creates its own energy and it matches the phase. This blue line here is the director's contribution to the primary red signal. And as the director's signal goes rearward, the reflective element creates its contribution, the light blue line, and they both join together to make the signal stronger in that direction. This is your main lobe. Conversely, in the back, you have destructive interference, where because this element is longer, this is it actually disrupts, it slows down one of the waves, has a slower wave that actually cancels out some of the energy, cancels out the energy from the director and from the driven element. So this destructive interference reduces the signal to the back. It works the same way on a received signal. Obviously, the waves would be coming toward the antenna, but it has the same effect. It reduces the strength of the signals from the rear, and it amplifies the signals it's receiving from the front. So you had some answers to some of the questions there. The approximate length of the driven element in the Yagi is a half a wavelength, just like a dipole. How do the three elements compare? The reflector is longer, the rear element, and the director in the front is short. And you can see that this antenna is sort of like an arrow point. The director in the front being smaller and the reflector in the back being larger. This is a 4 element, same principle. You've got some labels here of the other elements, but they aren't part of the test. Physical length of the boom, the number of elements on the boom, and the spacing of the elements on the boom all contribute. And they can all be adjusted to optimize the gain forward, the front to back ratio, which is the resistance to the signal from the back, or the SWR bandwidth. In other words, can this antenna work for the entire width of the band that you have your privileges in? Or is it too narrow for that and you have to limit your use, or you suffer a poor signal if you go outside the best bandwidth of this Yagi antenna? All of those things are part of the formulation of this antenna. So when you lengthen the boom and add directors, the gain increases. You can keep going a long way. If you increase the diameter of the elements, each of these elements, you can actually make the bandwidth of the antenna wider. In other words, the width of the area of the band that you have the lowest SWR, the lowest standing wave ratio, the closest to resonance. Another thing that's a question on this test is, how does antenna gain in dBi compared to gain stated in dBd? Your answer is dBi is higher, because when you show a realistic model of an antenna, you assume that since it's all based on a dipole, you can't count this 2.14 that you get theoretically when you go from an isotropic point, this I, to this element. You're 2.15 dB stronger than that isotropic point, because you're focusing the energy in two directions. In this gain antenna, these other elements further focus it. So you want to always look for the dBd indicator. Now, since these antennas are directive, you need to know which way to point the antenna. So one of the questions on a different part of the test in the section 2 is, what is this azimuth projection map? Well, it shows you the shortest direction to the location you want to point your antenna at. So we have one here that's local. This is obviously centered on me because I'm the center of the world from where I sit. But unfortunately, this world map down here is centered in the Central Valley, and it really doesn't matter but it's not centered on my house because it would look exactly the same anyway. So as you can see, Europe is northeast of us, pretty almost northeast. It is not due east like you might think. Excuse me. Okay, we talked about comparing gain already. Omnidirectional radiates in all directions. Decibels are that unit of power. Hang on just a second. Front to back ratio is the ratio between the forward signal strength and the reverse signal strength. So how can you add even more gain? Well, we talked about adding more elements to the boom, but there is an advantage to vertically stacking 2-3 elements as opposed to having a single 6 element. And here's the reason. It narrows the main lobe in elevation. Remember that critical angle that Tim talked about? Now this is focusing these antennas into a narrower critical angle rather than having a broader spread of energy. They're focusing it in this small energy, and they're focusing it closer to the horizon, which gives you that lower critical angle so you can hit that F2 layer further away. Get that long skip. Making the boom longer would not narrow that elevation angle, but it would narrow the azimuth, making it more difficult to aim that antenna exactly toward the station you're trying to receive. And you can see by this next question that you gain about 3 dB by adding 3 more elements. You essentially, this boom length plus this boom length is about 3 dB, and you've added 3 more elements as well. So we're going to shift over to feed lines now. You have to get the energy to the antenna. First thing you're going to be tested on is the characteristic impedance of the parallel conductor feed line. How is it determined? Well, it's determined by the distance between the centers of the 2 conductors and the radius of those conductors. You only need to know that much. In terms of window line, or ladder line is sometimes referred to, the distance between these conductors and the ratio of the diameter of those conductors gives you a 450 ohm impedance for window line. Now there are the questions. Both of these are expressed in ohms. Now, it's useful to have different feed lines with different impedances. You see coax is 50 or 75 ohms, window line is 450. You can have a ladder line of 600 ohms. It depends on what kind of antenna you're feeding and how you're going to match that to your radio. Modern radios are designed to work with coax. Coax, as you know, has a shield on the outside and a conductor in the center. The shield on the outside is grounded, so that coax is what we call unbalanced. Window line does not ground one side of the 2 conductors. It is what we call balanced because both conductors carry the same voltage. Neither one of them is at ground potential. That makes it contributes to the feed line being lower loss, but it also makes it sensitive to the proximity of metal objects like rain gutters or towers or masts and things like that. Because feed line does attenuate, in other words, reduce the amount of energy that actually gets to your antenna. one of the questions, how does attenuation in coax cable change with increasing the frequency? Well, it increases. The higher the frequency, the more the attenuation. Remember, coax has that continuous insulator that separates the center conductor from the shield on the outside. That I believe that continuous insulator in there actually slows down some of the energy and turns it into heat rather than putting it on the antenna to be radiated. So what units of the RF feed line loss usually expressed? Decibels per 100 feet. And you see a little chart here that shows that. I want to draw your attention to the fact that as the coax increases in size, it's less lossy. Here's your RG58U 50 ohm coax at 100 megahertz, which is almost 2 meters, not quite. Come on back. 4.5 decibels per 100 feet. That's more than half of your signal being dissipated in heat. However, the RG8, which is the same impedance, but twice as large in diameter, loses a third as much in heat. However, if you can use open wire line, you're down to 0.3 decibels. And as you can see, the attenuation increases with frequency. The higher the frequency, the more the attenuation. That's also a question on the test. So standing waves. Standing waves happen in all kinds of wave formations, but we're talking about the radio signal that we're sending out to the antenna. In this graph, the radio signal that we're transmitting is red, but the coax feed line, or whichever the feed line it is, the feed line impedance does not exactly match the impedance of the antenna. Remember, the impedance of the antenna varies a little bit with the frequency, because it may not be resonant exactly at the frequency you're on right now. It's affected by the height, it's affected by a lot of things. So you never have quite a perfect match. So you're getting some energy. The blue line is the energy being bounced back to the transmitter because there's a mismatch between the impedance of the feed line and the impedance of the load, the antenna. Well, as it bounces back, there are points where the two cancel each other out, like right here. However, unfortunately, there are points when they add. And this black line represents the added energy or the neutral energy. That added energy is a higher voltage than the energy you're sending out to the antenna because of the addition of the returning energy. This high voltage spike can actually damage your radio. Most of your radios will actually start reducing their own power if this spike from this standing wave gets too high. So you have a couple of questions here, and I've got the questions in here now. You know what causes it? It's because of this difference in impedance. And what can you do about it? Well, you try your best to match the impedance of the antenna to the feed line. And this is how that ratio is calculated. Both of these questions are on the test. You can see that one of them is a high resistance load compared to your 50 ohm coax, and the other one is a low resistance load, perhaps a very short antenna compared to your 50 ohms. They both yield a high standing wave ratio. Feed line loss. Remember we talked about feed line loss increasing with frequency and increasing with length of the feed line? Well, when you add to that the standing wave ratio loss, because there is a loss from not getting all of that energy into your antenna, that's wasted energy that bounces back. So a high SWR increases the loss in a lossy coax and a lossy transmission line. So if you start with the lossy transmission line like RG58U, very small, and you add a mismatched antenna, you'll be lucky to get much energy at all out to that antenna. We're going to go into matching a little bit further, but the first thing I want to point out is you can have a really bad antenna. One of your questions is, what is the characteristic of a random wire HF antenna connected directly to the transmitter? Well, I have a question for you. Where is the random wire resonating? It's random. You don't know where you're connected to that antenna. If you're connected to the end of the wave, the middle of the wave where the impedance is low. So you may be connected to the high voltage end or the high current end. In either case, you shouldn't use an antenna like that unless you put an antenna tuner between the radio and the antenna to keep too much RF from coming back into your radio and back into you. I have had an RF burn, and they are not funny. Antenna matching. That example and this example here is an antenna tuner between the feed line and the radio will have no effect on any mismatch between the feed line and the antenna impedance. You need to remember that. It's also a test question from one of the other sections. And here you're tested on your knowledge of if the SWR in the antenna feed line is 5:1 and the matching network, this right here, at the transmitter end of the feed line is adjusted to show a 1:1 standing wave ratio. That's perfect. To the transmitter, what is the resulting SWR on the feed line? Well, you start with 5:1, you've still got 5:1 on the feed line. You've just fooled the transmitter into thinking that you've got a balanced load because it's only balanced in this box, or a matched impedance. It's only matched in this box. What is the effect of the transmission line loss on the SWR at the input of the line? Okay, you've matched it right here. Well, it's still, because your feed line gets even lossier with a high SWR, it masks the real SWR that you're going to see in the meter at your transmitter. So the higher loss reduces what you can measure. It doesn't reduce the SWR. It reduces what you can measure. It's a double bad thing. So how do you match antennas? Well, here's two examples from Yagi's. The first one at the top is a beta match. This is an example of a balanced match. Both sides of the dipole are insulated from the boom. So this dipole is balanced. The match is balanced because it's at the 0 voltage point. It's grounded, but it's equal voltage on both sides. You can't see it, but this antenna is actually being fed by a balanced transformer. So the unbalanced coax goes in the other end, and it's actually made out of coax. And it comes out as a balanced signal so that it matches perfectly with this antenna. You can make a beta match like this out of a piece of feed line, and you can often just use a moving shorting bar here to actually fine tune the match. It doesn't have to be solid like this. It can be something that's clipped on to both sides. In the lower example, the gamma match is ideal for coax because the driven element is actually bonded to the boom. It's at 0, it's grounded. So you're only matching one side but because it's a dipole, it still works. You've got signal coming through both sides, and it works. And grounding, being able to fasten the driven element to the boom eases the construction process, because you don't have to insulate it and create a separate thing, because the center of the reflector and the center of each driven element can be bonded to the boom. No problem. Okay, just for giggles, what's some other impedance matching methods? Now, you've already been told that you can adjust the proximity to ground in your ground plane antenna to make your 15 ohm impedance. Do you recognize the J-pole here? Somebody bent it, but a J-pole is a half wavelength with a quarter wavelength matching stub, and you move the connection point up or down in this stub to get your 50 ohm match when you tune your J-pole. These two dipoles have different feed points. They could both be multi-band dipoles, but it's easier with this off-center fed dipole here because it has harmonic resonant points that are tapped into right here. But now this is a higher impedance because it's not in the center of the dipole anymore. So in most cases with an off-center fed dipole, you have a 4-to-1 balun to have a 4-to-1 match ratio to change that from a 200 ohm antenna to a 50 ohm match with the coax. When you have a standard dipole, you often should use an onion, an unbalanced to unbalanced choke, because one side of your coax is grounded to one element and the other side is hot and connected to the other element. There is a mismatch in the voltages on both sides, and you could get a standing wave ratio, or I'm sorry, you get a current coming down the outside of your coax. That extra current can get back down into your radio, and you can get RF into the radio. So this choke, this onion, will block that. It's not really a matching device. It's a kind of a resistor for that returning energy on the outside of the coax. Okay, a little bit of fun here with the specialized antennas. We've got a log periodic. This antenna uses alternating pairs of elements that are tuned for different frequencies to become a multi-band antenna. It has a wide bandwidth and it's multi-band, up to 10-to-1 ratio, which could actually be almost from the 80-meter band to the 10-meter band in one antenna. So it's rotatable. You got two questions about this. And I did not put the question here, so you need to look them up in the back of this PowerPoint. Multi-band trap dipoles. These traps use an LC circuit, an inductive capacitive resonance circuit, to either inductively load an element to make it longer, which is what happens with the 40-meter dipole. These loading coils on each side actually fool this antenna into thinking it's longer than it really is when it's got a 40-meter signal coming through it. However, this 15-meter coil is resonant, and a resonant circuit is an open circuit on an antenna, so it stops the signal of a 15-meter signal stops right here at the coil. But the capacitor in here will allow the 20-meter signal to go through that coil. It gets a little bit of inductance and gets a little bit longer, but it stops it at the capacitor of the next loading coil, or the next trap. I'm sorry, not loading coil, trap. So this is a really clever way to have a single pair of elements that handle multiple bands. However, one of your other questions is, what's the downside of a multi-band antenna? It has poor harmonic rejection because remember, 20 and 40 and 15 have a harmonic relationship. 7 megahertz, 14 megahertz, 21 megahertz, a third harmonic of 40 meters. What about mobile antennas? They're really short, right? At least on HF. Well, you got two examples here. One is, what direction is this halo? Well, this halo is a half wavelength dipole. However, it's wrapped around in a circle. So what direction is the maximum radiation of a dipole? It's perpendicular to the elements, right? Well, but this one's wrapped in a circle, so it actually becomes an omnidirectional horizontal antenna. What about this screwdriver, this vertical here? How are we going to make this 8 or 9 foot long thing resonate on the HF bands? It's because the coil, you've seen a coil, it looks like the thread's on a screw. There's a motor in the bottom, it twists the coil. There's a traveling conductor or contact that goes up that coil connected to the whip on top. And so you can lengthen or shorten that coil and load the base. Make it resonate with whichever band it's designed to tune for. A couple other specialized antennas. Most of us haven't ever even seen a beverage antenna. This one is several wavelengths long, and it's a primarily receiving antenna, but it's apparently a pretty high gain receiving antenna and has less noise than many others on really low bands. Now we have another loop. This loop is a small loop. This is not a full-size half wave. This is a tenth of a wavelength in circumference or less. So it does not radiate perpendicular to the elements. It has a null perpendicular to the element or in line with the elements. I'm sorry. No, I'm sorry. The way they word this question is kind of backwards. Which direction or directions does an electrically small loop, this one under 10th of a wavelength, have nulls in its radiation pattern? And this one, the nulls are broadside to the loop. It receives in the line of the loop here. So you can use this antenna for finding signal sources in the plane of the loop. You've heard a lot about NVIS antennas. Which of the following antenna types will be most effective at or near a vertical incident skywave antenna for short skip on 40 meters? So this is a 40-meter dipole placed a tenth to a quarter of a wavelength above the ground. Remember that diagram? This is the diagram repeating itself. A tenth is the blue one. Most of the signal strength is going up and being reflected.
I just want to throw in something here, and that is regarding the plans for test sessions. Fort Bragg on November 4th, Ukiah on November 11th. Both of those are Saturdays. So get that on your calendar. We'll probably be asking you to sign up for the test session, at least the Ukiah one. So I know who's coming. I print out the paperwork ahead of time, but get it on your calendar. And we look forward to putting this educational experience to use.